Namaste, everyone. Today we're going to dive into something really fascinating called Markov Networks. Now, you can think of them as a kind of special map, one that reveals all these hidden connections between things. And I promise, by the end of our little chat today, you'll know exactly how to read this map.
Okay, so here's our plan. We're going to tackle this in 4 simple steps. First up, we'll get a grip on the core mathematical rule. Then, we'll see it in action with a simple example, a network of 4 friends. After that, I'm going to let you in on a little secret, a shortcut I like to call the nosy neighbor rule. And to wrap it all up, we'll compare these Markov networks to their famous cousins, the Bayesian networks. A nice, clear path for us to follow.
All right, part 1, the rule of independence. Now, before we start looking at any of the simple pictures and graphs, we first need to understand the one mathematical rule that really powers this entire thing. You could say this is the engine under the hood.
So let's just set the stage a little. Imagine imagine it's your entire extended family at a big wedding. Every single person there is a variable. Now, from this huge family, we can make smaller groups, right? Let's say group X is all the uncles, group Y is all the aunties, and group Z is all the children. They're all part of the big family U, but they are their own distinct groups.
So, here is the core idea, the mathematical heart of it all. We can say the uncles, our X, are independent of the aunties, our Y, if we already know about the children, our Z. Now, mathematically, this is true if and only if we can break our probability formula into 2 completely separate parts. Just look at it. One part only involves the uncles and children, X and Z, and the other part only involves the aunties and children, Y and Z. See how there's no part that directly mixes uncles and aunties? That separation, that clean break, is the mathematical proof of independence.
That was all a bit theoretical, no? So now, let's make this abstract rule very, very concrete. We'll take a super simple example of just 4 friends and see exactly how this whole factorization thing works in practice.
Okay, meet our 4 friends, A, B, C, and D. Take a look at the connections in the graph. A is friends with B and D. C is also friends with B and D. But, notice something? There's no direct line between A and C. Now, the formula you see on the right, that describes the entire friendship dynamic. Each of those little phi parts, we call them potential functions. They basically just measure the strength of the friendship, the connection, between the friends it links, like between A and B, or B and C, and so on.
So, how do we find the hidden relationships here? Well, it's actually just like basic algebra. We're just going to rearrange and group the different parts of this formula. For our first try, let's put everything that has to do with friends A and C on one side, and then we'll see what that tells us about friends B and D.
And here we go. This is what we get after grouping. Look at the new formula. We've basically collected all the parts that involve friend B into one nice bracket, and all the parts involving friend D into another bracket. So the first new function is all about B's relationship with A and C, and that second one, it's all about D's relationship with A and C. Do you see it? B and D are now in separate mathematical containers.
So what's the big reveal? By splitting the formula this way, we have one big function that's only about B, A, and C, and another big function that's only about D, A, and C. It's like B and D are in completely separate mathematical worlds, yeah? They're only connected because they both know A and C. And that means B is conditionally independent of D, given we know about A and C. We found a hidden independence just by doing a little bit of algebra.
But wait, we're not done yet. The way you choose to group the formula actually matters. So let's try grouping it a different way and see if we can find another hidden relationship in there.
And there it is. This time, we've bundled all the parts with friend A together and all the parts with friend C together. And what's the result? Well, now we've proven that A is independent of C, just as long as we know what's going on with B and D. It's the same formula, just a different grouping, and we've discovered a completely new independence.
Phew, okay. That was a lot of algebra, wasn't it? All that rearranging and grouping, it can be a bit tedious to do every single time. But what if I told you there's a secret, a little shortcut that lets you find these independencies just by looking at the graph? No algebra needed. Sounds good, right? And this brings us to my absolute favorite part. I like to call it the nosy neighbor rule. Now, the official fancy name is the Markov Blanket, but our name is a bit more fun, and it's a beautifully simple, intuitive shortcut for seeing these hidden connections.
So, what is this Markov blanket? It's actually very, very simple. Just look at the diagram. You pick any person, let's say the red dot in the center. Their Markov blanket is just their immediate neighbors, the blue dots they are directly connected to. Think of it as their inner circle of friends, the people they talk to every day. And here is the nosy neighbor rule itself. Any person is independent of everyone else in the network, as long as you know what's happening with their immediate neighbors. Let's say our red dot is Sharmaji. If you want to predict what Sharmaji is going to do next, you don't need to go and survey the entire neighborhood. No, you only need to talk to his direct neighbors, the blue dots. Once you know about them, asking anyone else all those black dots gives you absolutely no new information about Sharmaji. It's that simple.
Now, just to make sure this idea is absolutely crystal clear in your mind, let's do a quick comparison. Let's put our Markov network side by side with its very famous cousin, the Bayesian network. I think this comparison will really highlight what makes Markov networks so special.
So, have a look. The key difference is right there on the screen. On the left, a Bayesian network. See the arrows? They show a direction, a cause and effect, kind of like a parent-child relationship. Intelligence leads to your grade. But on the right is our Markov network. No arrows, just simple lines. This shows a symmetric relationship, more like being neighbors. A is B's neighbor, and B is A's neighbor.
And this brings us to the most crucial point of all. In a Bayesian network, what a node depends on is its parents. But in a Markov network, as we just learned with our nosy neighbor rule, what a node depends on is simply its neighbors. Parents versus neighbors. That, right there, is the fundamental difference.
So let's quickly summarize our entire discussion today. First, we saw that we can prove independence by factorizing or breaking apart the probability formula. Second, we learned the easy way. The Markov blanket is just the node's immediate neighbors. Third, this neighbor rule is the key defining property of a Markov network. And fourth, this is very different from the parent rule that we see in Bayesian networks. 4 simple, clear takeaways.
And I'll leave you with a thought to chew on. Now that you understand this simple neighbor rule, just think about where you could apply it. How could it help us understand friendships on social media? Or maybe how a single pixel in a medical image is really only influenced by the pixels that are directly surrounding it. You see, the applications for this are absolutely everywhere. Thank you for listening.